So we're working in with section 16D is what we're calling this. And this is going to be some word problems, solving those with exponential and logarithmic equations. So we can model growth and decay with the same types of functions. So it's usually a number a times e to the kt. Now, the key thing is to look at the value of k. So if k is greater than 0, it's a growth. If the coefficient in front of your time and your exponent is greater than 0, it's a growth. If k is less than 0, it's going to be a decay. That's the thing to keep in mind. So e to a positive power is going to be a growth. E to the negative power is going to be a decay. We're also going to work with some money problems. So compound interest, stuff like that, those will always be growths. So here we're talking about half-life. So half-life is the time it takes for half of the atoms of the substance to disintegrate. So if you start out at 100 units, after its half-life, you'll only have 50 units left. So half-life of carbon-14 is 5730 years. We want to determine the value of K in the equation of decay. So for the most part, use the decay function. What I tend to do with these half-life problems, I tend to just say that A is 100, and then that Y is 50, because it doesn't really matter. It's all percentage based. So they've just plugged in a variable. They've just said A and then half of A. So it's okay to pick numbers. I mean, you could pick 50 and 25 or 10 and 5. It doesn't matter, because ultimately we're just using it as a percentage as that it's going to be half. So because once you divide, we're just left with what that percentage is. So 0.5 is e to the, we know it's a decay, so you have to use a negative k. So negative, we know the time this time, so negative 5730k. Since it's e to a power, we take the natural log. And then we just divide by the time to get the value of k. So if we're trying to determine the half-life of plutonium, we use that same basic decay function. It's a decay because it's half-life, you get less of it. So again, I'm just going to say we started out with 100, and so then if it's a half-life, we're left with 50. So I know it's a decay, so k is going to be negative. So I have to make sure to do negative k times my time of 24,000. So then I can divide, 50 divided by 100 is 0.5. So get e to the negative 24,000k. Take the natural log of both sides. That undoes that e to the power. So we're just left with the exponent. And then divide. So our k is going to be the natural log of 1/2 divided by negative 24,000. It's going to be a really small number. We got 4 zeros here and then about a 289. So we can also use these types of equations to do some carbon dating. Okay, so we want to see how much, it's saying that the amount that remains after t years is 2%. So what I think about it is, if we started at 100, that means there's only 2 left. The key though is that you're going to be dividing, and you're going to write your percent as a percent, or as a decimal over here, and then solve from there. But these are also decay functions, so they'll work the same way as the half-life problems. So here we've got this formula. A is the initial amount of carbon-14, T is the number of years, and Y is the remaining amount. So if we think, how old is a fossil? That is lost 95%. So if it's lost 95%, that means that only 5% is left. So when I set up my equation, I say, if I started at 100 grams or whatever, there's 5 left when I started at 100. So e to the negative 0.00012 t. So then you can solve. So you would divide by 100, and then you take the natural log of both sides. So you'd end up with natural log of 0.05 is going to be just the exponent part. And then you can divide. So your time ends up being the natural log of your percent left, so 0.05, divided by your coefficient 90.00012, which is about 24,964 years old. So How old is a skeleton that has 95% remaining? So instead of 5 on the left-hand side, we're going to have 95. So when you divide by 100, you'll end up with 0.95. So eventually we'll get to the natural log of 0.95 is the negative, all those zeros. T, and then T is the natural log of 0.95 divided by the coefficient. And this fossil ends up being 427 years old. So we're going to use that same equation. We're going to say a specimen that originally contained 42 milligrams now contains 8. So how old is the fossil? So we have what's left, 8 is equal to our original amount, 42, e to the negative 0.00012 t. So now you divide by 42. You'll get some kind of decimal, but I tend to leave it as a fraction so I don't have to worry about those rounding errors. So then you're going to solve this the same way we did the other ones. Take the natural log of both sides, and then you'll have to divide by that coefficient. So t is going to be the natural log of 4 divided by 21 over the coefficient, and you get an answer of about 13,819 years old. Woolly mammoth specimen was thought to be about 12,000 years old. How much carbon-14 should be in the animal? So we're trying to see what's left. So I'm going to call it Y. That's how much we're looking for. So let's say we started with 100%. So I'm going to say, or 100 grams, whatever, with my coefficient here. And then my time I know, and that's 12,000. So once you plug in those values, you find out that Y is 23.7. So remember the way I have it set up, I'm kind of talking about it in terms of percents. If I started at 100%, 100 grams, how much do I have left? So that 23.7 represents, it has 23.7% remaining after 12,000 years. So these are populations, they're representing growth. So the only thing that's different is that you're going to have a positive K. So just pay attention to the problem. If it's saying it's a decay, your K will be negative. If it's a growth, your K will be positive. So a type of bacteria is growing exponentially according to the model. If there are 1,000 cells initially, it's 1,650 cells after 40 minutes. Find the value of K. So Y is how much we have after the time. So that's 1,650. Is 1,000, what we started with. E to the K, that's what we're looking for, times time. So time is in minutes, so we can just use 40. So divide by 1,000, you get 1.65 is e to the 40k, again positive k. So take the natural log of both sides, divide by your coefficient. K is going to be the natural log of 1.65 divided by 40. K values are usually pretty small. K ends up being about 0.0125. Now this one's a tough one. Suppose a second type of bacteria is growing exponentially according to this different model. Determine how long it will be before the number of cells of this bacteria exceed the number of cells in the other bacteria. So we have to take this equation, 0.0432t. We want to see when its number of cells will be greater than the previous one. So take that K value that we used and do this. So I'm going to divide both sides by 50 so that I get a whole number on the other side of 20 e to the 0.0125 t. Wow, now when we take the natural log of both sides, over here we're just going to be left with our coefficient or our exponent. When I take the natural log of both sides here, I'm taking the natural log of a product. Well, when you take the natural log of a product, you can rewrite it as a sum. So I take the natural log of 20 plus the natural log of e to the 0.0125t. Well, natural log of e to the 0.0125t is just going to be 0.0125t. So we can subtract our t's. We get 0.0307. T is greater than ln of 20. And then divide. And t has to be greater than about 97.58 minutes.